Begin with the problem description first. I don't think the image in the first paragraph is relevant to the problem, and I haven't seen this anime as well, so I don't know how it's related. At least please let me know it's somehow related. And so starting off the second paragraph, it explains what is the median, which is kind of pretty standard. Basically means the middle element. If the subarray is an odd length, and if it is an even length, that will be the middle two. Take the average of the middle two. And the max of the array is the minimum excluded positive integer that is not inside that subarray. So a subarray is good if the max of that subarray and the median of that subarray are equal. And then there's also another terminology called permutation P. So for example, permutation P equals 3. It means all the order you can get from 1 to 3. So for example, 1 to 3 is one permutation, 3 to 1 is one permutation, and 3, 1, 2 is one permutation, and 2 and 3 is another permutation. So out of our permutation, we want to know the number of subarray inside any permutation that are good with a value x, and then we'll iterate this value x from 1 to n. So it is the example put here. This one, the first integer is the number of test case, and there are 5 integers, 1, 2, 3, 4, 5, and each integer represents n, and then n means we will go from 1 all the way to n for iterating it. So for example, when n equals 3, that means we have to return 3 result. The first result means x equal 1, and the second result means x equal 2, and the third result means x equals 3. So let's take a look at x equals 2. So x equal 2 in a permutation of 3. So 1, 2, 3 means 1, 3 is one of the good subarray in this 1, 3, 2, because when you add 1 and 3 and divided by 2 will be 2, and 1, 3 again, but it's from a different permutation. And 3, 1, we will just sort this subarray, and then it will be the same as 1, 3, and 3, 1 again, but from a different permutation. So in total, there are 4 good subarrays. And if you take a look at the constraint, the n can be really large, like from 10 to the power 5. So it means that for getting each number, for example, getting this 4, it should not take linear time. It should take logarithm time or constant. That's pretty much all for the problem description. And let's think about can we actually solve. So let's take a look at the first hand. Let's think about when will good subarray have the value of 8. A good subarray of value 8, first, x must not exist in that subarray because we want the smallest missing positive Vx. So if x is inside that subarray, then it will not be having the good value of x. So what other ways can we achieve the good value of x? Well, we can do something like this. If we somehow manage to put x minus 1 and x plus 1 in the middle, then we will take the average and we'll get the value of x. But there's not the only one, you might ask. For example, x minus 2 and x plus 2, we can also have the good value of x. But if you think about it, even if there is more arrangement, can get the median of 8. But for example, if x minus 1 also does not exist in the subarray, then the minimum missing positive will be x minus 1 instead of x. So it turns out x minus 1 and x plus 1 is the only way that we can go. So if we only look at x minus 1 and x plus 1, you can see 1 all the way to x minus 1 must exist. Because for example, if something like 2 does not exist in here, so the minimum missing positive will be 2 instead of x. So x minus 1 elements must exist in here on the left hand side. And then we also want x plus 1 because otherwise we cannot get the median of. And after x plus 1, another x minus 2 element must exist as well because we want to put x minus 1 and x plus 1 in the middle of the subarray after sorted. So that's pretty much the condition of a subarray. So let's see how can it help us to solve the problem. So from the above diagram, we can tell that for a good subarray of value x, there must be 2 times x minus 1 element inside the subarray. And then for this 1 to x minus 1, that's pretty much fixed. There's not much we can do. X plus 1, there's also not much we can do. So the remaining, what is the length for this segment? That will be 2. There will be 2 times x minus 1 because that's the length of the whole subarray minus x minus 1 means the length of this fixed subarray, and then minus 1 again for this x plus. So we still have to choose something for this red segment. So what can we choose? Well, basically we can choose anything that does not exist in here. So n minus x minus 1, and then for this segment, and then minus 1 again for the x1, and then minus 1 again. You might ask, what is this? So minus 1 again is for the x because we cannot put x in here because one of the requirements says the minimum missing positive must be x, so we cannot include put x in here. So therefore, there's like an n choose k problem. N is this, all the elements we can choose, and k is this, is how many positions we can place inside this rect segment. And is that the end? No, because the subarray order does not really matter. That's why if the length is 2 times x minus 1, there will be factorial 2 times x minus 1 subarray. So we have to multiply that as well. But is that the end? It's still not. There's one more thing. So from the above, we just consider how we can pick and permute the good subarray, but there are some remaining elements after choosing that subarray. For example, after choosing this good subarray, let's assume this good subarray is something here. I will just mark it as purple, the bracket of purple. This will be the good subarray. There's a lot of elements inside, and the remaining element can be A and B and C. And as you can see here, if the remaining element is free, they are like 4 positions for us to place the good subarray. So we have to multiply that as well. And also the remaining element, it can be in arbitrary order as well. So we have to multiply the factorial of the remaining as well. And that's pretty much all for the solution overview. Let's see how can we actually implement through the Cook implementation. Here I do some modularly inverse in order to have this choose function. It's basically calculate the n choose k in the modular p, but this is not the main idea of the problem. So the main idea of the problem is this function. It will return the number of good subarray with value x in an n permutation. So first I'm going to check if x minus 1 or x plus 1 does not exist. If it does not exist, as we discussed, this is the only way that we can get the good value of the x is from x minus 1 and x plus 1. So if they do not exist, then we just turn 0. And otherwise, as we discussed, 1 all the way to x minus 1 and x plus 1 already selected. So the remaining is x plus 2 all the way to n. So the remaining option, so what is the length? The last will be n and the first will be x plus 2. And then the last minus the first plus 1 is like the standard way to calculate the length of this range that we have to select. And then the space, as we mentioned, it is the remaining space inside a good subarray. So the total length for the good subarray will be 2 times x minus 1, and then we minus x minus 1 for the 1 all the way to x minus 1, and then we minus 1 again for the x plus 1 because they are already fixed. And then again, if there's some boundary case there, it just returns 0. Otherwise, for the remaining options, we will run n choose k, where n will be the remaining options for us to choose from the array, and then k will be the remaining space in that subarray. And then after that, the order of the subarray can be arbitrary, so we have to multiply it with the factorial. And there are n minus 2 times x minus 1 elements left unchosen. So this 2 times x minus 1 is the length of this subarray, so n is the length whole array. So the remaining will be like the whole array minus the length of this subarray. So the order of that remaining can be arbitrary as well. So we have times it with the factorial of that. And also, it also provides us remaining plus 1 gap for us to lay the subarray. So we have to times it with remaining plus 1 again, and then eventually we just return the answer in the modular. And then this is how we're going to read the test case. So I'm not going to go through them one by one. Basically, you just read all the test case and then iterate x value from 1 all the way to n, and then get the good count of that, and then just return all the answer eventually in here. So that's pretty much all. Let's try to submit problem. Okay, accept it. And let's go through the type and space complexity. So for space complexity, indeed we have to store the factorial and inverses up to 10 to the power of 5. So it will be on, and n will be the maximum number that we can see from the input. And the time complexity will be constant because we have already calculated all the things. So you can see in count here, we didn't do any loop in here. All the things inside is just constant. So it looks pretty long because I added a lot of comment and I try to separate out each operation, but it is just a formula kind of solution instead of looping it, if that makes sense. So in total, for each count code, it will take constant time, and the recalculation of the factorials and inverses will be on. So GPT-4 got this analysis correct, and that's pretty much all. We'll see you next time. Bye bye.